Fire is not a wild, untamed force. It is a rule-bound chemical process, an energy system that can be observed, measured, and controlled. At a molecular level, this reaction is called combustion. It triggers only when a material reacts with oxygen in the air. This reaction forces a rapid release of energy, which produces two distinct, measurable outputs, heat and light. Mastering this chemical engine, knowing the exact conditions that force it to start and stop, is the first step to harnessing its power safely. But the combustion system cannot run on just any material. It demands a specific set of physical inputs. Materials capable of catching fire and acting as fuel, like paper, wood, and petrol, are categorized as combustible substances. By contrast, non-combustible materials, like solid stone or metal, reject the system. They refuse to react with oxygen, even when exposed to intense heat. Identifying and isolating the correct fuel is the foundational requirement for creating any controlled combustion environment. If paper and wood are highly combustible, we have to ask why they sit completely stable at room temperature. This chart shows ignition temperature, the lowest thermal threshold required to force a substance to start burning. Different fuels possess vastly different ignition temperatures. While solid wood requires a massive input of heat, liquid fuels sit far closer to the danger zone. Extreme outliers such as petrol or LPG are classified as inflammable substances. Their ignition temperatures are so dangerously low that a single spark can instantly trigger the reaction. Knowing a material's specific ignition temperature allows us to accurately predict fire behavior, assess threat levels, and design industrial safety protocols. Once you cross that thermal threshold and achieve ignition, the actual energy output is entirely dependent on the fuel. We quantify this output using a metric called calorific value. This is the exact calculation of heat energy produced by the complete combustion of 1 kilogram of a given fuel. This graph ranks baseline fuels against high-efficiency modern alternatives. The difference in scale is massive. Wood generates roughly 17,000 kilojoules per kilogram, coal pushes past 30,000, and LPG maximizes output at 55,000. Selecting the optimal fuel for a system is a matter of balancing initial combustibility against maximizing this calorific value for peak efficiency. The speed of combustion dictates its form, ranging from the steady burn of a gas stove to the explosive force of fireworks. By isolating a standard rapid combustion flame, like a candle, we can map the physical structure of the reaction and see exactly where the energy is concentrated. The flame's dark inner zone is starved of oxygen, trapping unburned vapors. Moving outward, the yellow middle zone undergoes incomplete combustion, producing limited heat and leaving carbon particles behind. But the thin blue outer zone has full access to atmospheric oxygen. This guarantees complete combustion, making the outer edges the absolute hottest part of the system. The visible color and structure of a flame are not random. They serve as a direct diagnostic readout of the reaction's efficiency and oxygen supply. When this chemical system scales out of control, suppressing it requires a systematic elimination of one of its required inputs: fuel, heat, or oxygen. For standard reactions involving wood or paper, deploying water is effective because it rapidly drops the material's temperature below its specific ignition point, shutting down the loop. But deploying water on an oil fire creates a catastrophic failure. Because oil is lighter, it floats directly on the surface of the water, rapidly spreading the active chemical reaction across a much wider area. For liquid and electrical fires, the primary solution is a carbon dioxide extinguisher. Because carbon dioxide is heavier than oxygen, it operates through a different physical mechanic. It sinks rapidly, blanketing the fuel source and physically severing the fire's oxygen input. True mastery of combustion means observing the variables. It requires knowing the exact inputs to start the chemical engine and exactly which link to break to stop it.